And now we're in for a doozy when we're looking at chirality. So we've set up structures, how to draw them with different relationships and kind of seeing those pieces. And what we're about to encounter in chirality is one of those kind of quirks that is obvious and virtually impossible to see all at the same time. Right? So where this really kind of came to forbearance is with this particular molecule, thalidomide. And the concept of it really came about when we look back with, I believe it's Louis Pasteur, and he isolated, I can't remember it, but a chiral molecule from wine. And so what ends up happening is these molecules have very differently results on their environment. So let's take a look to see what's going on when we're talking about with chirality. Come on, click. Chiral versus achiral. So this is relatively simple as a definition, but the application of it becomes very, very challenging. So we have to be a little bit careful with it, and you will see questions that really pin you down on the definition and not like the use of it. So be careful with this. Some structures have kind of a handedness, okay? And according to this, we're saying all structures. The relevance comes into play as to what that handedness is. For instance, a pencil has a handedness. It could be used in either the left or the right hand, so it's really ambidextrous as far as the hand. But if we switch to, say, scissors, well, scissors have a handedness associated with them. They're designed for the right hand or they're designed for the left hand, and that becomes very challenging to kind of switch back and forth between them. So that kind of directionality, does it have a preference of one hand over the other, or does it use both, is our chiral versus achiral. So chiral is that it prefers one hand over the other. Achiral is that it can be used in either place. Okay? So the chiral definition comes back to this superimposability. Okay? It's saying that we are non-superimposable on the mirror image. So if we go through and take a look at a right hand and we look at the mirror image, okay, we put a mirror right here and we looked at it, it would look like my left hand. Are those superimposable? And so one of the things that we'll commonly get is you go, oh yeah, of course they're superimposable. See, they overlapped. No, they didn't, okay? Because when they overlapped, is the top of my right hand overlaying with the top of my left hand? No, they actually aren't. To superimpose, I would have to align them this direction. The thumbs aim opposite directions. So those are actually non-superimposable. We're not swapping them, slapping together. Oh yeah, I can clap, and so that means it's achiral. No. You have to, every aspect has to layer perfectly in the same space. And your hands can't do that. That means your hands are chiral. They are non-superimposable on the mirror image. This is why scissors are also chiral, because you can use a pair of scissors in your right hand, and if you try to use them in your left, it freaking breaks your fingers. Right? Achiral molecules are superimposable on the mirror image. For instance, a pencil, if you draw the mirror image, you can just turn it to align for that mirror image. There's just a simple rotation. There's not a handedness associated with it. Chairs, very commonly, are achiral. This aspect of seeing it in the real world, you might be like, well, it's not that big a deal, hands versus chairs. Well, it comes into play with molecules as well. And so there's a new notation showing up in here. We've got that squiggle line. That squiggle line is really saying that we're not defining whether that is a wedge or is that a dash. Okay, so the squiggle says we could be doing either. We haven't really nailed that down. Okay? And if we look at that, just wedge or dash, that wedge or dash is actually dictating a handedness of the molecule. Well, how important is that handedness? Well, thalidomide was a very important drug that came about in the 1950s that cured morning sickness. So women, when they're pregnant, have issues of vomiting and getting sick. Thalidomide was the drug that was used to make them not sick. Great, fantastic. But it had that handedness associated with it. wedge versus dash. Which way is it going? Okay, or that bond aimed. Chemists at this time knew about chirality, knew it existed. They just didn't understand how important it was. Thalidomide, unfortunately, brought that importance to bear. That simple switch between it being a wedged conformation coming towards you, rather, or dashed going away, made all the difference between that drug preventing women from getting morning sickness. I think I said that right. So not getting sick. And the other conformation was a mutagen. Right? Meaning the pregnant women are ingesting a mutagen where their fetus now gets exposed to a mutagen and it mutates the baby, right? And in not nice ways. So you can look up stories about it. It's an infamous kind of study of chirality and its vast importance. Thalidomide is not unique. If you've heard of ibuprofen, or naproxen, I think it's naproxen. S-naproxen versus R-naproxen, those are referencing different handedness of the molecule. That different handedness does different things. One of those forms cure the pain. The other form is an acute liver toxin. Who knew? Kind of a big deal. We don't want to just give everybody this drug. Oh, great, you don't feel your headache anymore, but don't worry, we'll find you another liver. Like, that's kind of a big deal. So this handedness came about and we really kind of acknowledged its importance, and we said, okay, when we go through and make drugs, we have to take this into consideration. Why do we have to take it into consideration? Virtually everything on a molecular level within biology is handed. Okay, be it this right or left hand, depending on how you want to reference it. And we'll come up with a better naming system for that handedness potentially in the next unit. Okay, so it's an important thing. We need to be able to acknowledge it. Because of that handedness also, though, I need to be able to name things differently, right? You heard me saying R-naproxen, S-naproxen. There's a new nomenclature system that then is associated with this, which means we have to be able to identify them, right? How difficult is it to really see this? Okay, so we talked about wedged versus dashed. Well, look in the upper right-hand corner. Right, what do we got? We got two molecules, they're both wedged. So if we were going to go through and classify them according to our system, we might go through and say, well, they're both wedged, they're identical, dude. This was a stupid question. Okay, this is why this is challenging. Okay, so if I've done this correctly, yeah, I think that's right. We look at that. That should be the upper left molecule, right? With the red ball aimed at you. Cool, there it is. Okay, and magic, ta-da! All I'm gonna do is spin it around and ta-da! Now we have the molecule in the upper right, right? There's a thing with the R, and you're like, well, I can't really tell if that's aimed at me or away. So this is where it's helpful to throw in a hydrogen at that position to help accent it. So let's go ahead and accent that, okay? And it's the same molecule, so I only really have to put on one connection, okay? So we look at it, ta-da, there it is. There's that one, and there's the hydrogen in the back, right? Okay, and well, why not? I made a second one, right? And we'll show that these indeed superimpose. Okay, and this is kind of small, so let's go ahead and make this picture bigger so we can see it a little better. If my mouse would work, there it goes. So boom. Okay, you always wanted to see more of me. Ugh. Heaven forbid. Whoops, I turned it the wrong way. Boom. Boom, right? There they are. So I kind of like the chlorine aimed up, so I'm going to leave that one alone. So there it is. I want to take this molecule and I want to make the chlorine aimed up. So like, ta-da, Mike, that was easy. It's aimed up. Okay. Is it now superimposable with this structure? Well, if we go through and look, the carbon backbone is indeed superimposed, right? We start kind of low, we go up, we go down, we go up. Nice little zigzag. So we could go through and show that superimposability. But when we go through to show that alignment, anybody notice an issue about that red ball and the white ball? They aren't the same. They're aimed differently. This one has the red ball aimed to the right, and this one has it aimed to the left. And that's kind of odd. Well, let's just fix that. Right? So now they're aimed the same. Okay, so clearly superimposable. Let's turn it back around. And you saw no tricks. There's no sleight of hand. Do the carbon backbones now align? These molecules do not superimpose. Wait a second, but you said they were identical. They look identical. They're both wedged. That doesn't make them identical. Right? That wedge all depends on your frame of reference of the molecule. And when we go through and look at that frame of reference, it can change things. It's the same deal as your hands. Okay? So this molecule is chiral. Okay? It is not identical to this one. Even though they look incredibly similar, they're different. Okay? Which means if they encounter a chiral system, say like my hand, they're going to interact differently. So when I grab it this way, I can get the red atom aimed out. But if I try and grab the same, I get the white atom aimed out. Okay? So we're getting a different interaction. That interaction can cause major issues if you're doing drug design, and it can cause all sorts of side weird things if you're looking at other aspects. So how does this apply out to the rule set that we've already seen? Okay, well, we've got our flow chart, same molecular formula, yes. Superimposable, no, so they're not identical, so they're isomers. And now we move to that same connectivity. Well, do they have the same connectivity? The chlorine is still connected to position 2. If we went through and attempted to name these, we should achieve the same name. It's 2-chlorobutane. We would number 1, 2, 1, 2. Okay, so same atom connectivity is yes, because they have the same name. That means these structures are stereoisomers of each other. Okay? As stereoisomers, it turns out you can get a whole lot of other things popping out of this. But before we get there, first we want to address what's happening here. It is that carbon, okay, that important carbon that's causing this issue, okay, where that wedge is located. So we want to be able to categorize that particular site and say, why is that causing me problems? Okay, so before we really push into this, what we're really looking for is something known as asymmetry. So the molecule has to be asymmetric, like your hand is asymmetric. If we cut it in half, okay, I don't get a thumb popping out over there. Okay, so there's a little bit of asymmetry associated with it. Okay, that's the important part. We've seen asymmetry before. We can reference it with what's known as geometrical isomers with our cis and trans, with our alkenes, because those have the same atom connectivity, but those R groups are aimed opposite directions or they're aimed the same direction. Okay? Those are geometric isomers. While we did have cis and trans as a possible naming cis and not naming a cis and trans description for our ring structures, the ring structures will actually fall more into the chiral definition. Okay? And we'll look at that when we see some examples. So what is going on with that chiral system? Really what we're saying with a chiral molecule is that we have an atom that has 4 distinct groups. Okay, so when we looked at, well, let's take a look at this. Okay, we've got, whoops, we'll see why I had white on there in a second. Okay, we've got 4 distinct groups: white, green, yellow, and red. And that matches that bottom example, okay, where they're all different, okay? And if we tried to draw a mirror image of this, okay, so if we set up a mirror plane here and tried to draw the result, it would turn out that that result we can't superimpose on that starting structure, okay? And that's what's being shown directly above here, okay? If instead we had that white ball on there, okay, that represents the very top example. Now when we draw that mirror image across, okay, we would have a symmetry axis so that all we would have to do would be turn the molecule around, and now it would superimpose. So it is that superimposability that makes it achiral. If it is non-superimposable, that's when we encounter the chiral thing. Where do we typically see that chiral atom show up? Well, wherever we have a carbon, or really an atom with 4 distinct groups connected to it. And that's what this drawing is trying to show, 1, 2, 3, 4. Right? If we go back to our 2-chlorobutane structure, did that really have 4 distinct groups? Okay, well, let's go through and take a look at it. What are the groups connected to that carbon? We've got red ball, white ball, black ball, black ball. 2 black balls. Right? How does that make this chiral? Can you tell a difference between these 2 black balls? You should be able to say yes. One of them has another black ball connected to it, while the other one does not. So because we can tell a difference between them, those 2 black balls are technically different from each other. And it is that difference that makes this chiral, because now it has 4 distinct groups connected to it. So your baseline easy way to determine chirality in organic chemistry is find a carbon that has 4 distinct groups connected to it. Distinct can be challenging because where do you find that difference? You continue to trail out until you find it. You could go out 20 atoms. If you find the difference, go all the way back to the origin and it's chiral. Okay, so look for those 4 different things. But remember, at the same time, it's not just 4 different things. It has to be non-superimposable on the mirror image. There are plenty of cases where we have something that doesn't have 4 distinct things, but is still non-superimposable on the mirror image, like your hand. Okay, so you still have to remember the definition of chiral. This 4 different things is a cheat to kind of get you through it a little bit faster and a little bit easier in most circumstances. Not all. Come on. Why? Oh, fine, whatever. So the other thing that you can kind of do, or I'll see reference to, textbooks like to reference this, and I get some people, oh yeah, planes of symmetry. Okay, look for planes of symmetry, because if there's a plane of symmetry, then the molecule will be achiral. Okay, but you have to see the plane of symmetry, and that's where things become problematic. It is not always easy to see a plane of symmetry. So for instance, if we start with this molecule, do you see the plane of symmetry? Okay, well, what's being trying to show at the far left is that that plane of symmetry is right here. And if I take a piece of paper and cut this molecule right through this axis and cut these atoms in half, then reflect across, well, that's a plane of symmetry. That's what it's referencing. Okay? If we moved over to a chiral molecule, we'll find that there is no plane of symmetry. Okay? The problem with this method is that if you don't see the plane of symmetry, you say it's chiral. That doesn't mean it's chiral, it just means you didn't see it. Okay? So I would argue that if you're being placed into a position of chiral versus achiral, you should really fall back on the hardcore definition, non-superimposable on its mirror image. That involves a whole lot more work, redrawing, manipulating, seeing 3 dimensions to be able to answer it, but it guarantees you're right. The process of finding planes of symmetry or an atom with 4 different things connected to it isn't always right. The 4 different atoms, probably 60% of the time. Plane of symmetry, maybe another 20%, okay? Which means 20% of the time, you get it wrong. And even that is a little bit unfair because that 20% is probably the most common test question. Okay? So in your homework, you'll be able to use 4 different atoms to define a chiral carbon quickly. In the homework, you might see a plane of symmetry one. Okay? But in the homework, you'll probably only see one that falls back on the hardcore definition. Exams, that hardcore definition ups or increases in activity or as far as appearance. And so you need to be a little bit more careful there. Okay, so just be aware of that going into it, and hopefully that'll help you out and move you through. Okay, so let's look at some examples and try and find those mirror planes, okay, or not mirror planes. So first and foremost, we're going to see an issue in the very first example here. What's that issue? Well, the issue is that we decided not to show a wedge or dash. Okay, should we have shown a wedge or a dash? Well, really the only reason we need to show a wedge and a dash is if there's a chiral center. Does that mean if there's no chiral center, we don't show wedges and dashes? No. Okay. If we go through and look at this structure, that starting structure, what we should be able to go through and do is acknowledge all the different things that are in here. See how I'm drawing in all those hydrogens? Remember how I said implied hydrogens will be the bane of your existence? Here it is. These hydrogens are identical to each other, which means not a chiral atom. These hydrogens are identical to each other, which means not a chiral atom. These hydrogens are all identical to each other, not a chiral atom. If we look at that blue position, we have hydrogen, bromine, red carbon with 3 hydrogens, purple carbon with 2 hydrogens. That is a chiral center. Okay? That should show a wedge and a dash. Okay? Or at very least a wedge for the bromine, and we could imply the hydrogen. Why did we not show it? We're trying to hide that information. And it's not so much that we're intentionally hiding that information, it's that very commonly students and faculty will not specify that wedge and dash. Okay? Not out of malice, but just accidentally leaving it off, which means we don't see it until it's too late when someone gives birth to a mutant child. Okay? That's a problem. Okay? So what we need to be able to do is to test your ability to look at that and be like, well, dang, that should have been labeled with a wedge or a dash on that bromine to specify which chiral atom we had. Okay? So just seeing a wedge or a dash doesn't mean it's a chiral atom. Not seeing one also doesn't mean it's not a chiral atom. Okay? Next one underneath, where's the mirror plane? Okay? Well, finding that mirror plane can be a challenge. So I would argue that I would just go through and be like hydrogens, hydrogens. Those are all the same. Hydrogen, hydrogen. I have 2 things that are the same. 2 things that are the same. At least 2 things that are the same. Okay, so I don't satisfy my my 4 carbon rule. That's going to be fine. Probably achiral. The biggest check that I should go through and do, so I could first do that, answer, if I got time, double back to it on the exam and be like, okay, let's draw the mirror image. So here's my mirror. So as it reflects across carbon, we go up, down, up. If we try to directly superimpose that over the top of this, hopefully what you see is that it doesn't superimpose, right? Okay. But if we take this structure and we rotate it, we would get that. That rotation is now superimposable on this. Okay? So you're going to be doing these 3-dimensional manipulations and rotations. It is incredibly easy to do these manipulations and rotations with a model. It is much more difficult to do it with the 2-dimensional drawing, particularly if you happen to be of a gender or really upbringing that didn't expose you to 3-dimensional thinking through 2-dimensional drawings, like things like Legos. And unfortunately, men have a distinct advantage here because we were raised with that tendency. That means all the more reason that women need to be using model kits to really push this. If you grew up with Legos, you're probably set, right? Because you understand a little bit more of that spatial reasoning. But right now, when we're looking at these drawings, all you're seeing is a flat thing. It's only when you make it 3-dimensional, and that 3-dimensionality has to happen in your head or with a model kit. Those are your only 2 options. And until you can convert that paper to your brain through the model all at once, you're kind of dead in the water and you're just guessing. Okay? You could probably get away with that. I'm not going to lie. You could probably just guess your way through chirality and just do really well everywhere else. Okay? But that spatial reasoning is something that's going to constantly come back. It just comes back with a vengeance with chirality. Okay? So we now need to be able to classify these things. Remember we said that these were stereoisomers? Okay, well, we're going to encounter some other categories that could potentially pop up, particularly if we have more than one chiral atom. Okay, so chiral atom, stereocenter, chiral center, stereogenic center, all equivalent as far as I'm concerned. Okay, and I will use them interchangeably. So we now need to deal with kind of these new labels. The first one that comes out is enantiomers. Enantiomers are two structures that are non-superimposable and are mirror images. To give you that mirror image idea, that first two molecules that we were looking at, these are mirror images of each other. Okay, it helps if I sort of, kind of, where that mirror is kind of running where my face is now. Okay, so they're mirror images. The relationship between these two guys is enantiomers. Okay, that's what they are. Okay, thalidomide, the two forms of thalidomide, they're enantiomers. Okay, as soon as you add more than one chiral atom, now you get into kind of new categories. Those new categories are our diastereomers, or as a lot of people like to reference them, disastomers. But since we're not in, that's an awesome face, since we're not in person, no one can actually say that, so we can all laugh at it. Instead, I'll just say it every so often so you can laugh at home, because OChem is funny. So disastomers are structures that are still non-superimposable, but are not mirror images. Okay? Meso compounds are structures that have two or more chiral atoms, but they are superimposable on its mirror image. But if they're superimposable on their mirror image, doesn't that make them identical? Yes, it does. So if you have two molecules that you think are identical, cool, do they have two or more chiral atoms? If they do, their relationship is meso, okay, or the relationship between those drawings is meso. The compound itself is known as meso, okay, and that would be kind of the end of it. That's all I got, okay. The big red flag for meso compounds is that you have an internal mirror plane and chiral atoms. Again, internal mirror planes are tricky. Sometimes you see them, sometimes you don't. Okay, so this now greatly modifies our diagram, and we end up with this now system where we still have our different identical and isomers, but those isomers now break down into structural, or isomers which break into structural isomers and stereoisomers. Our stereoisomers now split into geometric, diastereomer, and enantiomer, and we also see the meso pop up. I do apologize, those arrows didn't quite align the way I wanted them to, but they're pretty close. Okay, so what we'd be doing is moving through the flowchart to explain the relationship between structures. It takes practice. You need that practice. Okay, chirality does show up again when we predict products, but it doesn't come up with as nitpicking detail as we're seeing in chapter 5. Okay. With that, we're done with this section. We will move into, in the next video, looking at some examples of each of these, and then we're really done with this unit. So good job for sticking it out through another painful 30 minutes of me talking to myself.